Welcome to Study Loop.
This is problem number 38 of chapter 23. In this problem, we are given the diameter of an aperture inside of a telescope, and we're asked whether this telescope could resolve a binary star system given a certain angular separation. So the diameter given for the telescope is 2.4 meters, and the angular separation theta is given as 0.5 arc seconds. So first of all, let's go ahead and convert these arc seconds into let's go ahead and we can convert them to degrees or radians. Let's go ahead and convert them to radians. So first, how is an arc second defined? An arc second is defined 1 arc second is equal to 1 degree divided by 3600. So if we multiply this out, we're going to be in degrees because arc second cancels out with arc second. But we want to convert this to radians here. So pi radians is equal to 180 degrees. So when we multiply this out, we're going to get arc second cancels out with arc seconds. Degree cancels out with degrees. And all we're left with is radians. So let's see what we get for our angle when we multiply this out. We get a very small angle, approximately 2.4 times 10 to the negative 6 radians. Okay, so that's the angular separation. Now we are asked to see whether the telescope can resolve the binary system. So let's pull out the equation for Rayleigh's criterion. We have theta res. It's going to be equal to 1.22 lambda over d. In this expression, the unknown is lambda. So let's go ahead and solve for it. If we multiply both sides by d and divide by 1.22, we get lambda equal to d theta res over 1.22. So let's go ahead and plug in these values. Let's see what we get. When we multiply this out, here we're discarding the unit for radian. So that's why we converted here from degrees to radians, just so we could have a number here. And our final unit is going to be in meters. We're going to get 4.8 times 10 to the negative 6 meters, which is, well, 10 to the negative 6 meters, that's 4.8. It's going to be 4.8 micrometers. So this is the maximum wavelength that can be used to resolve this angular displacement. Any wavelength less than this should be able to fit through the aperture just fine to resolve this angular displacement. So for a telescope, the wavelength of interest are those associated with the visible spectrum. So the visible spectrum goes from 380 nanometers, so this is lambda vis, to 740 nanometers. Notice that lambda vis the wavelengths associated with visible light are much less than this lambda. They're much less because this is a micrometer, these are nanometers. So these are 10 to the negative 9, these are 10 to the negative 6. So the wavelengths associated with light are much less than the wavelength required to resolve this angular displacement here. So lambda vis is less than lambda. So can this telescope resolve that star system? Yes, because the wavelength associated with visible light is less than the wavelength needed to resolve that angular displacement.